Hello everyone. In today's class, we are going to discuss new chapter electric potential and capacitance. So in this chapter, first of all, we will discuss electric potential part and then we will discuss capacitance part. Now let's see it first topic everyone, electric potential energy. So what is the definition of electric potential energy? Electric potential energy is defined as the total work done by an external force in assembling a system of charges by bringing them from infinity to their respective location without any acceleration. So here work done by the external agent to bring a charge from infinite to the respective location. So whatever work that external agent is doing to bring a charge from infinite to the respective location, that work is storing as a potential energy in the system everyone. And here one thing is important, when we are bringing charge from infinite to a respective location, at that time acceleration should be zero. Correct? Because if acceleration is zero, then change in velocity is zero. And if change in velocity is zero, then change in kinetic energy is zero. Means whatever work you are doing, that work is storing as a potential energy. And we are interested here in the potential energy, not in the kinetic energy. That's why this point is important here, everyone. Acceleration should be zero. So note down this definition everyone, then we will do it derivation here. So now let's see it derivation everyone. So here we have two charges, Q1 and Q2. So let's suppose this is Q1 charge everyone and this is Q2 charge. And initial separation between these two charges is, let's suppose, R1. Correct? And here Q1 is fixed. Only Q2 can move and these both are positive. So initially this both charges is present at R1 distance, correct? Between Q1 and Q2 we have repulsive force. So due to this repulsive force, this Q2 charge will move toward the right. And this is the direction of electrostatic force. Electrostatic force is conservative force, correct? This thing we know that. So I am denoting with the FC everyone. It is the direction of electrostatic force. So due to this force, this charge is moving from R1 to R2 position. So initial separation between the charges is what it is, the R1. And now it is R2, correct? So position between this and this everyone, what it is, let's suppose this. And this distance is, let's suppose, x here everyone. Let's suppose at t equal to t time, this particle is present at x distance, correct? The distance is how much everyone? It is x. At that time, here force is Fcx. At x position, force between this Q1 and Q2 is what? It is a Fcx everyone. Alright. So here we want work done by the conservative force. If you will think everyone about this Fcx force, so this Fcx force is not constant. Say it, at the x position, if I will write force between these two charges, so this is what? This is K Q1 Q2 by x square. Correct? From the Coulomb's law, this thing we know that. So right now the force between these two charges is K Q1 Q2 by x square when it is present at x position. Correct? Now this x is continuously changing. When the charge particle is moving from R1 to R2 position, then this x is continuously varying here. Correct? That's why this conservative force is not constant here. It is the variable force. Correct? So it is the variable force and we want here work. How much work is done by the conservative force when the charge is moving from R1 to R2 position. So here we want work done by the conservative force. So what we can do it here everyone, we will find here work for the small displacement. So I am considering here small displacement is dx, correct? And for this small displacement, this force can be considered constant, everyone. So I am writing here dWc, correct? Work done by the conservative force for the very small displacement, and for this very small displacement, or we can say that for infinitesimal small displacement, this force we are considering constant. So that's why it is dWc is equal to conservative force at x distance into displacement in the direction of conservative force. What is the basic formula of the work, everyone? Force into displacement of point of application in the direction of force, correct? This is the basic formula of the work. So we are using here this formula, and I am writing work for the small displacement. Now I am putting here value of Fcx, which is k q1 q2 by x square d square. So this is the work for this small displacement. But here we want correct work for R1 and R2 position. How much work is happening due to this conservative force between R1 and R2 position? This thing we want. So here we need to put limit also, everyone. So I am putting here limit from R1 to R2. Okay. Now the next thing is what here? We need to do it integration. So do it integration on both sides, everyone. So integration of dWc is what? It is the WC. And now you can do it one more thing. K q1 q2 put outside the integration. R1 to R2, and 1 by x square can be written as x power minus 2 dx. This thing can be written as, correct? Now the next thing is what, everyone, here? If we will do it integration of x power minus 2, so it will be what, everyone? Think it. If we have algebraic function and the power is n, so it is x n plus 1 by n plus 1. So here x power minus 2 integration can be written as x minus 2 plus 1, so it is minus 1 divided by minus 1, and limit of integration is R1 to R2. Now you can do it one more thing, put negative sign outside this bracket. So we have minus k q1 q2, and x power minus 1 can be written as 1 by x. So this is 1 by R2 minus 1 by R1, correct? So now this thing we have. So work done by the conservative force can be written as, now put negative side inside this bracket, and finally we have k q1 q2, and this is R2, everyone. Upper limit minus lower limit. So we are multiplying negative side inside this bracket. So it is k q1 q2 1 by R1 minus 1 by R2. This is the work done by the conservative force, correct? This is the work done by the conservative force. See, here one thing is important, everyone. When we are moving this charge, at that time acceleration is 0. Now think it, everyone. In this scenario, acceleration is 0 or it is here varying. So because here conservative force is varying, so definitely acceleration is not 0 here. This right now this particle is accelerating, but here we want, correct? Here we want, everyone, net force on this particle should be 0. This thing we want, because we have required here acceleration 0. So in opposite direction, we will apply here external force. So here external force is equal to minus of work done by the conservative force. Both are equal and opposite, everyone. That's why we are putting here negative sign. So if conservative force and external force both are equal, correct? So here some external agent is applying force in the opposite of conservative force. That's why net force is getting 0 here. And if net force is 0, then acceleration is 0 here. And this is the required condition. Alright. So here we know one thing, everyone. Work done by the conservative force is equal to minus of work done by the external agent, correct? This thing we know, everyone. Work done by the conservative force is equal to what? Minus of work done by the external agent, because direction of force is opposite. That's why it is here we have negative sign between the conservative force and external force. So this is the reason of negative sign, everyone. That's why if I will write work done by the external force, so it is what? It is the minus of K Q1 Q2 by R2. So just multiply negative sign, correct, with this WC. So what you will get? K Q1 Q2 1 by R2 minus 1 by R1. This thing you will get. So what we are getting here, everyone, work done by the external agent is equal to what? K Q1 Q2 by 1 by R2 minus 1 by R1. We know one more thing, everyone. Let's say new page. We know this thing. Work done by the external agent is equal to change in potential energy from the work power energy chapter. And same thing we did in gravitational chapter also. So work done by the external agent is equal to what? It is the change in potential energy, correct? Okay, this thing we know. Now the next thing is what, everyone, because we are looking for the change in potential energy. So can I write del U is equal to, here we have K Q1 Q2 R2 by R1. K Q1 Q2 1 by R2 minus 1 by R1. Correct? This thing we have. Now take some conditions, everyone. So I am taking here condition. So R1 I am taking R, everyone, and R2 I am considering infinite. Correct? R2 is equal to, I am taking infinite, everyone. So here this R2 is what? It is the final position and it is infinite also, or we can say that it is U2 also. So U2 I am considering as a U infinite and this is the final position. So at infinite, potential energy is what? It is a zero, everyone. So remember it one thing, everyone, U infinite we are considering here zero, means potential energy at infinite position we are considering zero, and this is our reference point. So potential energy at infinite we are considering as a reference point, everyone. So at an infinite position potential energy is zero, and this is our reference point also. So this condition I am putting in this equation. Now let's see what we will get. So see it, everyone. Del U can be written as U final minus U initial equal to K Q1 Q2 1 by R2 minus 1 by R1. Now R1 is what is the R2 is infinite, and U final is U infinite, and potential energy at infinite we are considering zero, and it is our reference point also. So I am putting here zero, everyone. Correct? So it is 0 minus Ui equal to K Q1 Q2 1 by infinite. R2 is infinite here, everyone, and R1 is R. So what we have, 1 by infinite is again 0, everyone. So this is 0, minus minus will get cancelled out, and Ui I am considering U. So we are getting here U equal to K Q1 Q2 by R. Correct? So this thing we are getting, and this formula is important for us, everyone. When two charges is present at r distance, so potential energy between these two charges can be written as K Q1 Q2 by R. This is the formula, everyone, and this formula you need to keep in your mind. So when two charges present at r distance and we want to write down potential energy between these two charges, so formula is what? It is K1 Q2 by R. Correct? So write down this formula, everyone. Finally we got it, this, and this is the change in potential energy formula, and this is the work done by external agent formula. Correct? And work done by the conservative force, already we got it here. So lots of formula we have here, everyone, and all formulas are linked. Correct? There's some relation we have between this all the formula. So this thing we are getting. Now keep one thing in your mind, everyone. When you are putting Q1 and Q2 value in this formula, then always put Q1 and Q2 value with sign, everyone. Like if we have two charges, Q1 is plus 1 coulomb and Q2 is what? It is minus 2 coulomb. So Q1 we will put 1, correct, and Q2 we will put minus 2, and then we will put here separation between the charges. Whatever charges we have, whatever separation we have between these two charges, that separation we will write here, correct. If it is 1, so I will write here 1, and then we will simplify and we will get the potential energy between these two charges. Correct, everyone? So I hope this thing is clear, how this formula will work. So note down. Now let's see one question, everyone, on the basis of this concept, correct? So when we have two charges and it is present at r distance, then potential energy between these two charges can be written as k q1 q2 by r. So we are doing one question on the basis of this concept. Let's see it, everyone. So let's suppose we have one square, and at the corner of this square charges are present plus q, and here we have minus q and minus q, correct, and this is center, everyone. And at the center of the square also we have q naught charge. All right, and this is the point O. Let's suppose this is first, second, third, and this is fourth charge. So what we want to do it in this question, everyone, we want to move this charge from center to A point, correct? So we want to move this charge from center to A. So how much work external agent has to do? This is the question. So external work we want to find here, work done by the external agent to move a charge from O to O. This is the question. So question is very easy, everyone. We know that work done by the external agent is equal to what? Work done by the external agent is equal to change in potential energy, correct? And change in potential energy can be written as final minus initial. So first of all, calculate initial potential energy of this Q naught charge. So U initial can be written as what? What is the U initial, everyone? U initial is, first of all, I am writing between 1 and O. So it is K, Q, Q naught by. Let's see what is the distance, everyone, between the first and Q naught charge. Let's suppose this distance is x, everyone, and then Q naught and second charge. It is again x. This is x, everyone, and this is also x. So this distance is x, this is also x, this is x, and this is also x, everyone. This all distance are same here. So when I am writing potential energy between 1 and Q naught charge, so it is k q naught, k q q naught by x. And if you will write between second and Q naught, then it is k q q naught by x, everyone. Now write down between O and fourth charge. So on the fourth we have negative charge, that's why potential energy is negative. We need to put here Q1 and Q2 value with the sign. This thing we know that. So minus k q naught q by x. Then we will write potential energy between O and third. So it is at the third point we have again negative sign. That's why potential energy is negative. So minus k q naught by x. This thing we are getting, correct? All right. The next thing is what here? Yes, this and this will get cancelled out, and this and this. So this all are cancelling. So initial potential energy, what we are getting, it is 0. So initial is 0. Now calculate final potential energy, everyone. U final. So U final equal to, see this charge we are moving from O to A. So distance between 1 and A point, and distance between fourth and A point. It should be same, correct? And now this charge is present at A point. So let's suppose this distance is between the first and A point, distance is, let's suppose, y, and this distance is also y between the fourth and A, and distance between second and A is what? It is z, everyone, and distance between third and A is again z. So let's see it. If we will write here final potential energy, so it can be written as what? First of all, I will write between 1 and A. So it is K Q Q naught divided by X this distance is y, everyone, between first and A right now, correct? And then we will write between fourth and A point, and fourth we have negative sign, that's why here we will write minus K Q Q naught by y. Then we will write between second and A, everyone, and at the second point we have positive charge, so potential energy can be written as plus K Q Q naught by Z. And then we will write between third and A, so it is minus K Q Q naught by Z, everyone. Now this and this is cancelling, and this cancelling. So finally we have final potential energy is 0. So initial is 0 and final is also 0 here we are getting, and we know that work done by the external agent is equal to what? It is final minus initial. So final is 0 and initial is also 0. So work done by the external agent should be what? It should be 0. So finally we are getting work done by the external agent is 0, and this is the answer, everyone. Means if you want to move this charge from A to O to A, then work done by the external agent is what, everyone? It is 0, correct? Note down. Let's see next question, everyone. A charge Q1 is fixed at point O and another charge Q2 having mass m is kept at a distance of r1 from charge Q1. If charge Q2 is released, then find the change in momentum of charge Q2 when the separation between the charge is r2. So this is the question, everyone. Let's see it how we can do it. So what is happening here? We have two charges. Charge number 1 Q, and Q1 charge is fixed, everyone, at point O, and another charge Q2 having the mass m is kept at a distance r1. And we have Q2 charge. This Q charge is present at r1 distance. So initial distance is what between these charges? It is r1. If charge Q2 is released, then find the change in momentum of charge Q2. Now what we are doing, we are releasing this Q2 charge, correct? So definitely here we have some electrostatic force on this Q2 charge. Due to this electrostatic force, this Q2 charge will move from R1 to R2. Correct. So this is Q2 charge, but now the separation between the charges is what? It is R2. Okay. So separation between the charges is how much, everyone? It is R2. And mass of Q2 charge is what, everyone? It is m, and the velocity is what? It is v, correct? So let's suppose when this Q2 charge present at R2 distance, at that time velocity of this Q2 charge is v2. Here we want change in momentum of charge when separation between the charges is R2. So for the momentum we have required here velocity, means v2 we have required here. So let's see how we can find out v2, everyone. So if you will think here, between this Q1 and Q2 charge, only we have electrostatic force, correct? Here friction we are not considering. So here we have only electrostatic force, and electrostatic force is conservative force. And when work is happening due to the conservative force, then mechanical energy is conserved, correct? So here initial mechanical energy should be equal to final mechanical energy. And mechanical energy is the sum of potential energy and kinetic energy. So initial mechanical energy can be written as Ui plus I, and final mechanical energy can be written as UF plus KF, correct? What is Ui value, everyone? So initially charge is present at R1 distance. So initial potential energy can be written as K Q1 Q2 by R1. And initially Q2 charge in rest everyone. So initial kinetic energy is 0. And then separation between Q1 and Q2 is what it is R2. So the potential energy can be written as K1 KQ1 Q2 by R2. And when this Q2 charge is present at R2 distance and velocity is V2, then final kinetic energy can be written as half m V2 square everyone. So from here we will get V2 value. So now let's see what we can do it. V2 square can be written as what? KQ1 I am taking common here. So KQ1 Q2 1 by R1 minus 1 by R2 and 2 and the derivative we have m. So this thing we are getting. So this is the value of V2 square. So what is the V2 here? V2 can be written as take under root on both sides. So you will get V2. So V2 we will get if you will take under root on both sides. So it is this under root 2k q1 q2 by m 1 by r1 minus 1 by r2. This is the value of V2. So here in this question we want change in momentum everyone. In this thing we want. So let's see it now next what we can do it here. Change in momentum can be written as what everyone? This is final momentum minus initial momentum, correct? Final minus initial. So final momentum of this Q2 charge is what? It is mv2 and initial is 0 everyone because it is in rest condition. So just multiply with the mass and you will get change in momentum. So if you multiply this V2 with the mass, then you will get change in momentum. So finally we have m under root 2k q1 q2 by m 1 by r1 minus 1 by r2. This thing we are getting. This is the change in momentum everyone. So note down. Let's see next topic everyone. Electrostatic potential energy of the system. So here what is happening? Suppose we have a square and at the corner of the square charges are present. Q1, Q2, Q3 and Q4. Correct? And we want potential energy for this system. And let's suppose side length of this square is A. So this is also A. Alright. So here we want potential energy of the system everyone. So first of all what I will do it here, I will calculate number of pairs, correct? Number of terms or number of pairs. How many forming for this system? So for this we will use this formula everyone. Number of term can be find out from this formula n equal to nc2, number of combinations. And if you will solve this nc2 then it is n minus 1 by 2. N is what everyone, what is the small n value? It is the number of charges. So number of charges is how many? Here it is 4. So 4 minus 1 divided by 2. Then how much it is everyone? 4 minus 1 is 3. So it is 6. So number of term, or we can say that pair, we are getting 6 here. Correct? And let's see it. So first pair we have Q1 and Q2. Second is Q2 and Q3. Then Q4 and Q3. And then Q1 and Q4. Correct? And then Q1 and Q3. And then Q4 and Q2. So total how many pairs we have here? It is 6 everyone. So one by one we will write potential energy for this all the pairs and we will add. Then we will get potential energy for the system. So what we are getting here, let's see it. Potential energy of the system equal to, first of all I am writing between 1 and 2. So it is K Q1 Q2 divided by A. Then between second and third, it is K Q2 Q3 divided by A. Then we will write between fourth and third everyone. So it is K Q4 Q3 divided by A. Then between fourth and 1, so it is K Q1 Q4 divided by A everyone. Now between 1 and third, we will write. So what is the separation between first and third charge everyone? So if you will use here Pythagoras theorem, then this is A and this is A. So it should be what? Root 2A. So separation between the charges is how much everyone? Between 1 and third, it is root 2A. So here we will get plus K Q1 Q3 divided by root 2A. Let's see it next term. We will get K now between 4 and second. So K Q2 Q4 divided by root 2A. So this thing we are getting. So this is the potential energy of the system everyone. So write down everyone, correct? And I hope this thing is clear how we can calculate potential energy of the system. So we need to see it first of all, how many number of pairs is forming. So we will write first of all potential energy of this pairs, and then we will add this all, then we will get total energy of the system. So this is the procedure everyone. Let's see this question everyone. Three charges Q, TQ and minus Q are placed at the vertices of equilateral triangle. The net electrostatic energy of this configuration is 0 if charge Q is equal to. So here we want potential energy of this configuration is 0 everyone. Means we want potential energy of the system is equal to 0. So this thing we want. So what should be this Q value? This is the question everyone. What should be this capital Q? So we will get 0 potential energy of the system. So let's see it everyone how we can do this question. So if you want to write potential energy of the system, so what we can do it? First of all, we will see it how many number of pairs we have. So here total 3 pairs we have, correct? So we will write potential energy of this pair. So first of all, I am writing between Q and plus 2Q. So it is K Q 2Q divided by A. Then I will write between plus 2Q and minus Q. So this is plus K 2Q minus Q divided by A. Then we will write between Q and minus Q. So it is plus K Q minus Q divided by A. Correct? This thing we will get. So here we want 0 everyone. So put equal to 0. Now simplify this and let's see what you will get. Otherwise write in the next step. System potential energy we have required 0 here. And simplify this seat. So this is KQ 2Q by A and this is KQ minus Q by A. So simplify this and this term everyone. So you will get KQ Q by A. And here we have minus K 2Q square by A. Now this and this will get cancelled out everyone. Take common and put on the left side. So it will become a 0. This thing also you can do it. So finally what we are getting here, we are getting Q equal to 2Q everyone. Means if you want potential energy of the system is 0, so the capital Q value should be what? It should be plus 2Q everyone. So the correct answer is what? It is option number D everyone. So D is the correct answer for this question. Note down everyone. Let's see next question everyone. Two charges Q1 and Q2 are placed 30 centimeter apart as shown in the figure. A third charge Q3 is moved along the arc of circle of radius 40 centimeter from C to D. The change in potential energy of the system is Q3 by 4 pi epsilon naught K, where K is what? So in this question we want K value everyone, and K is not here Coulomb constant. So keep this thing in your mind everyone. K is not a Coulomb constant here, correct? So change in potential energy is given here Q3 by 4 pi epsilon naught by K, where K is not a Coulomb constant. Alright, so change in potential energy of the system can be written as what, everyone? It is final potential energy of the system minus initial potential energy of the system, correct? Now final potential energy, or now the initial potential energy of the system, if I will write, so it is what, everyone? So first of all, I am writing between A and C, so it is K, Q1, Q3 divided by 0.4. Then we will write between A and B plus K, Q1, Q2 divided by 0.3, correct? Then we will write between Q2 and Q3. So it is K, Q2, Q3 divided by 0.5, correct? If this is 30 centimeter, this is 40 centimeters. So it should be how much, everyone? It should be 50 centimeter. And if I will convert into meter, then it is 0.5. So this is the initial potential energy of the system. Now we will write final potential energy. This Q3 charge is moving in circular arc, everyone. And the radius of the arc is what? 40 centimeter. So it is moving from C to D. And this distance is how much, everyone? This distance should be also 40 centimeter. So this is circular arc. So this distance is again 40 centimeter. Alright, so now write down final potential energy of the system when this Q3 charge is present at D point. So let's see what it is, everyone. K, first of all, I am writing between Q1 and Q2. So K, Q1, Q2, and separation between Q1 and Q2 is how much? It is 0.3. Then I will write between Q1 and QD, everyone. Now Q3 charge is here, correct? At the D point. So it is K, Q1, Q3 divided by 0.4. Then between Q2 and Q3. Think it, everyone, what is the separation between Q2 and Q3? How much, everyone? It should be, say, total is 40 centimeter, between A and B is 30 centimeter. So this distance should be how much, everyone? It is 10 centimeter. So it is 0.1 meter, correct? So now we have U initial and U final. Now subtract this both because we want potential energy of the system. So if we will subtract this both, then what will happen here, everyone? This and this will get cancelled out, and this will get cancelled out. So now we have K, Q2, Q3 divided by 0.1 minus K, Q2, Q3 divided by 0.5, correct? Now do it one. Now let's see it next step, everyone. The space is less. Okay, see it, everyone. So now next what I am doing here, take K, Q2, Q3 common. Now remaining we have 1 divided by 0.1 minus 1 divided by 0.5. So you can do it one thing, multiply with 10 and divide with the 10. So what you will get? K, Q2, Q3. If you multiply with 10 and divide with the 10, then you will get 10 divided by 1. And here you will get 10 divided by 5. So it is 2. So we are getting finally 8K Q2, Q3. See, now this Q is what? It is the Coulomb constant. And we are not looking for the Coulomb constant. This thing should be clear. Correct? So, and Coulomb constant I am writing with a KB. So you will not get confused. I am putting here KB. So this is the Coulomb constant, everyone. There is a Coulomb constant. Coulomb constant I am representing with kV. Correct? So change in potential energy already we have, it is Q3 by 4 pi epsilon naught K. Correct? Now put value of Kb everyone, which is 1 upon 4 pi epsilon naught 8 Q2 Q3. Correct? So here in this question we have change in potential energy Q3 by 4 pi epsilon naught K. Correct? So with this Q3 by 4 pi epsilon naught we have K everyone. So with this 1 by 4 pi epsilon naught Q3 we have here 8 Q2. So this is what? This is the K everyone. And for this we are looking. So here what is the K value? It is 8 Q2. So compare this result everyone with given this equation in the question, then you will get your answer. So answer is what? It is 8Q2. So correct answer is options A. 8Q2 is the correct answer. So I hope this thing is clear everyone. Note down. Now let's see next topic everyone, electrostatic potential. So what is the definition of electrostatic potential? The amount of work done to move a unit charge from reference point to specific point inside the field without producing an acceleration. Correct? So in the potential energy, we have Q charge everyone. We are bringing Q charge from infinite to a specific point in the field. But when we are talking about the electrostatic potential, then we have unit charge everyone. And reference point meaning is what? We are considering potential energy at infinite equal to 0 as our reference point. Correct? So this thing already we know that. Infinite we are considering as a reference point, and there we are considering potential energy is 0. Correct? So what is the basic difference between the electrostatic potential energy and electrostatic potential? In the electrostatic potential energy we have Q charge, and when we are talking about the electrostatic potential, then we have unit charge everyone. Correct? So electrostatic potential can be written as what? It is the potential energy per unit charge everyone. And where Q naught is what? It is the unit charge. So energy per unit charge is what? It is the electrostatic potential. If you will see the unit of the electrostatic potential, so it is energy per unit charge. So unit of the energy is what? It is the joule, and unit of charge is coulomb. Correct? Or unit is what everyone? It is volt. Alright. And potential is the scalar quantity everyone. Keep this thing in your mind. Electrostatic potential is the scalar quantity, and electrostatic potential energy is also a scalar quantity. So write down this formula everyone and write down this definition. Then we will see it next slide. Note down everyone. Let's see it next topic everyone, electrostatic potential difference. So see it, what is the definition of electrostatic potential difference? The potential difference between 2 points in an electric field is the change in electric potential energy per unit charge when it is taken from one point to other. Correct? So what is the sense of this definition? Let's see it everyone. Let's suppose here we have electric field. So let's suppose this is the electric field everyone. And here we have 2 points in this electric field, point A and point B. Let's suppose this is initial position and this is final position. Correct? So this is initial position everyone, and this is final position. And let's suppose here we have Q naught charge at this A point, and we want to move this Q naught charge from A to B. Correct? So change in potential per unit charge is what? It is the electric potential difference everyone. So what is the del V here? It is del U by Q naught. So this thing we are getting according to the definition. Del V equal to del U by Q naught. So change in potential energy per unit charge is what? It is the potential difference between these 2 points. All right. Now the del U can be written as, from the definition, Q naught del V, everyone. Correct? Q naught del V. And the del V is what? Is the change in potential energy. So change in potential energy can be written as final potential energy minus initial potential energy equal to del U. And we know that one more thing, everyone. Change in potential energy is equal to work done by the external agent. Correct? So work done by the external agent to move a charge from A to B, equal to del U, and del U equal to Q naught Vf minus Vi. This relation we are getting, everyone, and it is very important relation for us when in the question potential, correct, is given. Let's suppose potential at A point and B point is given, and we are moving 2 coulomb charge from A to B. So how much work is required to move a 2 coulomb charge from A to B? If we have this question, so in this question we will put V initial and V final value in this formula and Q naught value, and we will simplify. Then we will get work required to move a charge from A to B, everyone. So like this we can do it. Correct? So when we have this type of question, so we will solve with the help of this formula. Note down. Now let's see one question, everyone, on the basis of this concept. A minus 5 coulomb point charge moved from point M at 10 volt to the point N at 5 volt. Calculate the work done by the electrostatic force. So here we want work done by the electrostatic force, everyone. Work done by electrostatic force we want here, everyone. So here Q value is how much? It is minus 5 coulomb. And point charges move from point M at 10 volt. So this is the initial position, everyone, point M. So this is Vi, everyone, initial potential. And point N is the final position. So this is Vf, correct? Final potential. So we knows work done by the external agent is equal to what? It is equal to change in potential energy, and change in potential energy can be written as Q del V, change in potential, which is Vf minus Vi. So this is the work done by the external agent, but here we want work done by the electrostatic force. So the relation between work done by the external force and work done by the conservative force is this, everyone. Correct? This relation we knows. So we want here work done by the electrostatic force or work done by the conservative force. So WC is equal to, put here negative sign. So we will get minus Q Vf minus Vi. Now the next thing is what? Multiply this negative sign inside this bracket. So you will get Q Vi minus Vf, everyone. So what is the value of Q here? Q is minus 5, everyone. So write down here minus 5. What is the V initial? It is 10. And what is the V final? It is 5, everyone. So 10 minus 5 is how much? It is 5. So 5 minus 5, 5 into minus 5, it is minus 25 joule. So finally we are getting, everyone, work done by the electrostatic force is equal to how much? It is minus 25 joule. So minus 25 joule we are getting, everyone. Now check here option. So we are getting option number C. So C is the correct answer, minus 25 joule. So I hope this thing is clear. Note down, everyone. Let's see next topic, everyone. Electrostatic potential due to the point charge. So here we want potential due to the point charge, everyone. Let's suppose we have plus Q charge. And due to this plus Q charge, we want potential at the P point. And the separation between the plus Q charge and the P point is, let's suppose, R. So potential at the P point due to the Q charge can be written as KQ by R. And here this Q value we will put with sign, everyone. Correct? If we have plus coulomb charge, then we will put here plus sign. If suppose here we have minus q charge, then we will put minus q. Then potential at the P point is negative due to this minus q charge. So here always put q value with the sign, everyone. Now the next thing is what, when we are writing this formula, everyone, then we need to keep one thing in our mind, everyone. At an infinite, we are considering potential energy is zero, everyone. So if potential energy at infinite is zero, then potential at infinite is also what, everyone? It is zero. And infinite we are considering as our reference point. So this formula is only valid if we are considering at infinite potential energy is zero. Then only we have potential at the P point is kq by r. All right. So keep this thing in your mind, everyone. Note down. Let's read one question, everyone, on the basis of this concept. Four electric charges plus q, minus q, and minus q are placed at the corner of the square of side 2L. The electric potential at point A, midway between the two charges plus q and plus q. So at this A point, we want potential, everyone. This A point is present between this plus q and plus q charge. So here we want a potential, and separation between plus q and minus q is what it is, 2L, everyone. Correct? So because side length of the square is given 2L, so this distance is L, everyone, and distance between A and plus q is what? It is the L. All right, so potential at A point we want. So let's see it, what we will get. So I'm writing potential at the A point, everyone. So first of all, I'm writing due to this plus q charge. This is first, this is second, this is third charge, and this is fourth charge. So potential due to the first charge can be written as at A point, it is K Q by L. Now potential due to this second charge at A point can be written as what, everyone? See, at the second point we have negative charge. So potential should be negative at the A point due to this minus q charge. So it is minus K Q by. Now we want distance between A and minus q charge. And what is this distance, everyone? If we will use here Pythagoras theorem, this is 2L, this is L. So this is how much, everyone? It is root 5L. Correct. So minus kq by root 5L we will get. Now due to the third charge at a point can be written as again here negative charge. So it is minus kq by root 5L. Then due to fourth charge at A point can be written as plus kq by L. Now simplify this. So we will get add this and this, everyone, first and last term. So this is 2k q by L and second and third. So minus 2k q by root 5L. This thing we are getting. Now do it one thing here. Take 2kql common, everyone, because it is present in both the terms. So 2kq by L we are taking common here. Now we have in bracket 1 minus 1 by root 5. This thing we have. Correct? So this thing we have, everyone. And if I will put k value is 1 upon 4 pi epsilon. So which options we are getting? We are getting option number B. So B is the correct answer, everyone. 1 upon 4 pi epsilon, 2q by L, 1 minus 1 by root 5. So this is the final answer. So I hope this thing is clear, everyone, how we can do it, this question. Let's see one more question, everyone, on the basis of same concept. 4-point charges minus 2q, plus 4q and 4q are placed at the corner of the square. What is the relationship between q and q? Make the potential at the center is 0. So at the center of the square, potential we want 0, everyone. So what is the relation between q and q? This is the question. So how we can do it, this question, everyone? First of all, write down potential due to this all the charges at the center, and then add this all and put equal to 0, because we want potential at the center is 0. That's why. And then simplify and you will get relation between q and q. So this question I want to give you a homework, everyone. Do it from yourself and put your answer in the comment box. And if you have a doubt in this question, any doubt you have, so put in the comment, about that we will discuss. So note down, everyone.